Okay, so welcome to our Cyber Physical Systems course, and today we're going to cover a summary of what is Chapter 5 on pervasive computing. Mainly I'm going to be giving you some highlights of the history, where the idea came from, and what is the state of the art of the technology and the concept, and what really do we mean by pervasive computing, and how the smart devices and components and services that we have been discussing in the previous chapters play into that. So with everything that you have been exposed to in the previous chapter, this concept really is an extension of all that we have been discussing, and it's not a complex concept or an extension to arrive at. Then in terms of tagging and sensing and controlling, we have discussed at least controlling and tagging with RFID to great lengths, and everything that we have been discussing in terms of sensing also applies here. And as I mentioned a few minutes ago, in terms of sensing, when we are sensing that natural world and we need data conversion because we are sensing it, and within the part of sensing, if we're doing that data acquisition in the world is analog, then we're going to be using data converters in terms of analog to digital converters. And if we are controlling something, we're going to be actuating part of that natural world that is also analog, so we're going to be using digital to analog conversion. So in that sense, I'm going to, as I mentioned, going to be going over some data conversion techniques, but not on the slides, but on the board instead. And that will wrap up the chapter. So we know that we have these cyber physical systems that by now you understand that are largely deployed and connected set of smart devices. Let's just let's call it that. And now that we have this technology available, we can reach back to all the way back to 1988. You guys were not born yet. And Xerox had a research center in Palo Alto near Stanford, and Mark Weiser, he envisioned this. He said, at some point, the computing devices would get smaller and more powerful and connected, so that you could have a network of these computing devices, which also would have some type of function, some function such as sensing something or controlling something. But then we have some inherent computing capacity capability, so that if they are on the network, you have this massive network of computing devices, and you could distribute computation, and they could aid each other with computation, so that you would have this pervasive computing environment as it was. So we already talked about the concepts of object to objects, thing to things, and different protocols that are available and widely used. So we know that Bluetooth is widely used to connect networks, and so recently the SIG, the special interest group that sort of manages the Bluetooth spec, they release a specification for mesh capability in Bluetooth. That is something new and exciting, and you should be aware of that, because up until now, if you wanted to set up a mesh type of, and now remember that we looked at different network topologies in the previous chapter, so you should know what a mesh type of network is in terms of the topology of the network. And if you wanted to set something up like that, you had to resort to Zigbee, which is sort of a short-range wireless protocol that did support, it was built to support mesh from the start, but it has evolved at a slower pace, mainly because it's an IEEE standard. And I don't know if I mentioned that companies tend to form consortia or special interest groups when they really want a technology and they don't want it to be slowed down by the slower governance process of adoption of standards of IEEE, which is more open, more inclusive, but it takes longer. So some companies they don't want to wait, and a lot of the most successful technologies have been done outside the IEEE umbrella, and some big companies just got together and said, we're doing this, and boom, we do it. That's the way that USB happened, spearheaded by Intel, and that's the way that Bluetooth happened. So, and they have both really been very successful. So Bluetooth, the SIG, the Special Interest Group, they announced the mesh capability. And the idea is that now you can come up with very large distributed networks. If each Bluetooth node can cover about 100 meters and they are connected in a mesh, even if one is down, you can get routed around it through the mesh, and you can really envision some really amazing applications with Bluetooth that is already very low cost because of the install base and the large volumes associated with it, and because it's going to allow this type of topology beside the previously available more constrained one for Bluetooth. So that's very exciting. And of course, beyond that, we have some other technologies that aid the massive connectivity and availability of computation from a pervasive perspective. So we have, of course, Wi-Fi, the XG type wireless communications or cell phone type of technologies, and the IPv6 capability to do multicasting in a huge outer space of many more bits than IPv4. So again, the idea is that you have all these devices and they can cooperate. So the key is, how do you define the different environments that this is applicable to? And then how do you deploy applications to the network? That is the challenge. How do you deploy software applications onto this available computing platform that is distributed? And you can start then looking at smart environments, and that would be more thing to thing or object to object. But then beyond that, we have human-centered environments that can be and can benefit from this pervasive computing capabilities, and just the regular distributed computing, which we know, and we had for a while. We know how to distribute software applications, let's say, on a network of servers or a network of workstations. That's not something new. What is new and challenging is, how would you deploy complex computational software to, let's say, a massive amount of cell phones that are connected in the network? They're simpler, but you have so many of them. How do you harness that computing power? So that's very interesting, and a very interesting challenge. So some examples, more futuristic in nature, of how this may look, there is the concept of smart dust. So smart dust would be very small devices that rely on MEMS technology. And these devices can range from millimeters to micrometer to nanometers, but they would have the ability to communicate with each other and have some computing capability, and the power will come from the numbers, not from a specific device. They would be limited in capability by themselves from a unique perspective, but if they can be integrated and connected, and also the range of communication would be very short, physically short, but then you have so many of them that you will be able to traverse a reasonably useful distance by just relying on the network and the topology and the connectivity. So that's the idea of smart dust. We also have the ability to integrate these devices into clothing and be able to harvest energy, kinetic energy from movement or from available light, from, if this is something that is with a human, from the thermal energy that humans generate. And the idea is that you could create this fabric area network at the personal or user level to provide some type of useful application, such as mainly in the, since we're talking about people, the first thing that emerges is the applicability to healthcare and wellness. So things like sports, fitness, stress management, some type of therapy, weight control, whatever. So things that are related to health and wellness through the ability to integrate these devices into clothing. That is not very far-fetched at this point with the technology that we have. Another technology that is actually, its development actually started in this area, OLED. So maybe about 15 to 20 years ago, it was a research project, and now it's widely commercialized. You can get organic light emitting diodes, or OLED versus non-organic that are based on silicon and some other fourth or fifth or third group compounds in the periodic table. These are organic light emitting diodes. They are lower power and they are flexible. So organic material lends itself to being fabricated so that it is you can bend it. It's not brittle. So that's another, from the perspective of putting things on people and being able to signal things. That's a technology that is already available and can be employed in this overall network of smart devices. Other technologies that are envisioned similar to MEMS is smart clay. So a material where these microstructures can assemble themselves and create interesting objects on the fly, such as electronic textiles and things of that nature. Once you have these devices, you have to really start rethinking the way that we, as humans, interact with these devices. So a big part of this, if you say, well, we understand that we have all this distributed and pervasive computing platform, but how do humans interact with it? So that's a big and open area of research, the whole human-machine interface, that how it's going to change from what we are used to, some type of touch screen or keyboard or things like that. So the idea is that if you now have all this technology that is intertwined in the fabric of what we do every day, our clothing, our objects, they're everywhere, then you have a technology that disappears because it's so pervasive and so integrated that you don't see it. And Mark Weiser back then observed that the most profound technologies are those that disappear because they weave themselves into the fabric of everyday life until they are indistinguishable from it. So that's a powerful thought, I think. So again, there are some slides on smart devices, but that's nothing new at this point, but it's there for completeness. And I do want you to read these few slides that I have in this chapter when they get put up on Canvas. Including smart sensors, which we talked about already. And that's basically it. That's all I wanted to say about chapter 5. I do want you to read the slides, and then I'll cover data conversion on the board until we're done with that topic. Okay? Great. Thanks.